picture the staging environment for a second.
Yeah.
You're building out this. You've spent maybe the better part of a year architecting this massive e-commerce platform for your company.
Right. Yeah. A huge undertaking.
Exactly. And the front end is, I mean, it's gorgeous. It's a beautifully optimized single-page application. The component library is just flawless. The state management is perfectly tuned. The whole user journey from, product discovery all the way to the cart is totally frictionless.
Hmm.
But then you hit the checkout component, and suddenly you're faced with this terrifying reality of capturing raw primary account numbers, expiration dates, and CVVs.
Yeah. The nightmare begins.
It really does.
Right.
Because the moment that raw card data touches your DOM, let alone your backend servers,
Yeah.
your PCI compliance scope just completely explodes.
Oh, absolutely. You're no longer just building a storefront at that point. You're suddenly managing a high target data vault.
Right. You got to secure the network layer, the application layer, the database, and then you have to prove all of that to auditors. I was thinking about this earlier. It's basically the equivalent of deciding to store radioactive material in your garage just because you want to power a reading lamp.
That is a perfect analogy. The liability footprint is just catastrophic for most engineering teams.
Mm.
I mean, the smartest architectural pattern we're seeing today, it isn't about building a more fortified database to house that payment data.
Okay, so what is the play then?
It's about leveraging data liability abstraction.
Yeah.
You want to set it up so your systems never actually handle the toxic payload to begin with.
Yeah.
The entire goal is to completely remove the merchant environment from the flow of sensitive data while still, and this is the tricky part, maintaining absolute control over the user interface.
Which brings us to the core of today's deep dive, and that is Collect.js. I really think of it as the ultimate sleight of hand in front-end development. It's this JavaScript framework that operates entirely on the client side. It captures the payment data, securely routes it away from your infrastructure, and just hands your application a harmless token in return.
Exactly. It's brilliant.
So for everyone listening, here is the mission for this deep dive. We are going to tear down the exact mechanics of this secure tokenization. We'll analyze the structural trade-offs between the two main integration paths, the lightbox and the inline methods.
We definitely need to dig into the CSS customization constraints too, because the security implications there are actually fascinating.
Oh yeah, we're definitely getting into the style sniffer and the CSS whitelist. And then finally, we'll decode how Collect.js normalizes payloads from modern digital wallets, like Google Pay and the notoriously strict Apple Pay ecosystem.
The recurring architectural theme you'll notice as we unpack all these mechanics is the tension. There's this constant tension between maintaining a pixel-perfect branded checkout experience and delegating 100% of the security risk to the payment gateway.
Right.
And Collect.js basically acts as the technical bridge negotiating that exact compromise.
So let's define the operational boundaries first, because the documentation is it's very deliberate about what Collect.js actually is, and maybe more importantly, what it isn't.
Yeah, that's a crucial distinction.
It is strictly a data collection and tokenization system. That's it. It is not a transaction engine. It doesn't authorize the funds or settle the batch or anything like that.
Right, it works as a specialized client-side interceptor. It feeds into your backend's existing direct post or payment API. Its sole function, really, its only job is to grab the sensitive input, encrypt it, send it to the gateway's level 1 PCI compliant servers, and then return a temporary proxy string back to your client.
And then your backend takes that proxy string, which is the token, and submits it to the actual payment API to request the charge.
Exactly. But the authentication model for this interceptor frequently trips up developers, especially backend engineers who are, heavily conditioned to treat all API keys as highly classified secrets.
Right, because usually if you leak an API key, you're basically handing over the keys to the kingdom.
Exactly. But Collect.js relies on a tokenization key, which is a specific type of public key generated in the gateway's control panel. And because the framework executes in the customer's browser, this tokenization key is injected directly into your front-end source code.
Which feels so wrong the first time you do it.
Oh, I know. It's entirely visible in the HTML script tag, which goes against literally every instinct a backend engineer has.
But in a public key infrastructure, that's exactly the intended design, right? Exposing the key is the only way the client can establish the encrypted tunnel to the gateway.
Yep. If someone inspects the network tab or they view the page source and they copy that tokenization key, they can't do anything malicious with it. It only has one direction of execution. It can only encrypt raw data into a token associated with your merchant account.
It's write only.
Exactly. It cannot decrypt data, it cannot process a refund, and it certainly can't initiate a transaction on its own. It's purely a write-only mechanism for token generation.
And the output of that write-only mechanism is the payment token itself. To your DOM, to your backend database, it's just an alphanumeric string. It usually looks like a randomized hash, something like, 34555 Zillion dash whatever.
Right. And the beauty of that is, if a bad actor manages to execute some crazy SQL injection attack on your backend and does a whole table full of these tokens, the data is completely useless to them.
Because the intrinsic value, the actual 16-digit Visa or MasterCard number, is langed away in the gateway's vault.
Exactly. Your server simply passes that meaningless string in a variable called payment token to the payment API. The gateway receives it, resolves the token back to the stored card data on its own internal network, and routes the transaction to the acquiring bank.
I want to talk about the lifecycle rules governing that token because they are incredibly aggressive, which is, a massive security benefit for you. First off, a Collect.js token is strictly single use. The millisecond you pass that token to the payment API and the gateway consumes it to attempt an authorization, the token is permanently invalidated, destroyed.
Which completely neutralizes replay attacks.
Right.
If an attacker somehow intercepts the network request between your server and the gateway and tries to resend that exact payload to run unauthorized charges, the gateway just rejects it immediately. The token literally no longer exists in its active registry.
But that also means developers have to handle their front-end state really carefully, right?
Oh, absolutely. Think about it. If a customer attempts a checkout, but the charge declines due to, say, insufficient funds, or maybe they just made a typo in their billing zip code, you cannot recycle that same token for the retry attempt.
You have to start over.
Right. The user has to trigger the Collect.js flow again to generate a brand new token for that second attempt.
And even if you don't use it, the token doesn't stick around. Like, say a user fills out the credit card form, Collect.js generates the token in the background, but then the user gets distracted, their dog barks, they walk away, and they abandon the checkout page without clicking the final submit button.
Right, an orphan token.
Yeah. That unused token automatically expires after exactly 24 hours. So as a developer, you don't have to worry about running cron jobs to clear out stale unused tokens on your end. The gateway handles the garbage collection automatically.
It ensures your system, and the gateway system, doesn't just accumulate this massive stockpile of theoretical attack vectors.
Now, for the actual implementation phase, before you even touch the front-end UI, the framework provides a really robust set of test tokens for your sandbox environment.
Yeah, these are lifesavers during a sprint.
They really are. It allows your back-end engineers to build and test the payment API integration long before the front-end team even finishes styling the Collect.js inputs. You can pass a string of solid zeros, just literally 0, 0, 0, 0, on, and the gateway treats that payload as a successful test visa card ending in 1111.
And there's one for ACH, too, which is great. If you pass a token consisting entirely of ones, the gateway processes it as an electronic check transaction for a test account under the name Jane Doe.
Oh, nice.
It's a fantastic way to validate your backend error handling, your routing, and your database logging without needing to manually type test card numbers into a front-end UI hundreds of times a day.
Okay, so moving from the back-end architecture to the front-end integration, this is where the framework presents two distinct UI paradigms. You aren't forced into a rigid, one-size-fits-all widget that ruins your branding. You essentially have a fork in the road.
Right. The choice between the lightbox and the inline integration methods.
Okay.
And honestly, that choice usually dictates how the engineering team approaches the entire checkout flow.
Let's start with the lightbox, because it is definitely the path of least resistance. It's essentially this heavily optimized modal overlay.
Yep.
You drop a single script tag into your document head containing your tokenization key, and then you just tag a standard HTML button on your page with the specific ID pay button.
Just camel case pay button.
Exactly. And when the user triggers that button click, Collect.js intercepts the event, it prevents the default form submission, and paints an overlay directly over your DOM.
And the lightbox handles all the input fields inside that modal. The pan, the expiration, the CVV, it's completely isolated from your underlying page layout.
From a deployment velocity standpoint, the lightbox is just unparalleled. Your front-end team doesn't have to write custom validation logic for Loon algorithms to check if a card number is valid. They don't have to manage the state of the expiration date dropdowns.
Oh, and they don't have to source and display the correct card brand SVG icons when a user types a 4 for Visa or a 3 for Amex. The Lightbox handles all of that client-side logic internally.
That saves so much time.
It really does. And once the user submits the data within that modal, Collect.js tokenizes it. It injects a hidden DOM node containing the payment token back into your original form and then programmatically triggers the final form submission to your server.
It's incredibly fast to ship, and honestly, the visual disruption of a modal can sometimes act as a trust signal for certain demographics of buyers. Like, it feels like a distinct, highly secure step.
Yeah, that's a really good point. Some users like that barrier.
But for modern conversion-optimized applications where brand consistency is paramount, you don't want a modal. You want the inline integration. This is what I call a stealth mode.
Stealth mode. I like that.
It allows you to build the payment fields directly into your existing form layout alongside your local field, like shipping address or email. So the user never feels like they're being handed off to a third-party pop-up.
The mechanism behind the inline integration is where the security architecture gets really, really elegant.
Oh man, the iframes.
Exactly. You still initialize the script tag, but you set the variant to inline. In your DOM, you place empty div elements exactly where you want the inputs to render, and you assign them specific IDs.
Like CC number, CSEX, CVV.
Right. Or you can do this for ACH checks using IDs like Checkabo for the routing number. When Collect.js initializes, it targets those empty div containers and dynamically injects full-width iframes into them.
And here's the magic.
Yeah.
Because those iframes are hosted on the payment gateway's domain, not your domain, the browser's native same origin policy kicks in.
Which is the bedrock of web security.
Exactly. Your local JavaScript, your state management libraries, your event listeners, none of them can cross that boundary. They cannot read the keystrokes, they cannot inspect the DOM inside the iframe, and they cannot access the raw values.
Right. The inputs look like they're sitting right there on your page next to your email input, but cryptographically and structurally, they are existing in a completely isolated sandbox.
It's the perfect exploitation of browser security protocols for the merchant's benefit. But injecting third-party iframes into a highly designed checkout flow usually results in a visual nightmare.
Oh, it's usually awful.
Right. Typically, you'd end up with fields that have mismatched fonts, different border radii, wildly different padding than your local inputs. You look at it and instantly know it's a clunky third-party widget.
But Collect.js solves this with what's known as the style sniffer.
The style sniffer is brilliant. Tell them how it works.
Okay, so instead of rendering generic, unstyled inputs inside the iframe, the script dynamically traverses your local DOM. It calculates the computed CSS of the surrounding input fields on your actual web page.
So it's looking at your local inputs.
Right. It reads the font family, the font size, the line height, the background color, and the border properties of your existing local form fields. It takes that calculated baseline and passes it through the iframe boundary to apply those exact styles to the gateway-hosted inputs.
So it basically forces the iframe contents to perfectly mimic the environment they were just injected into.
Exactly. The end user has absolutely no visual indication that the credit card field is communicating with a different server than the email field sitting right above it. It creates this totally frictionless, unified user experience while maintaining that ironclad security boundary of the same origin policy.
But as cool as it is, the style sniffer isn't infallible, especially if you have a highly reactive front end where styles change based on complex state logic, or if you simply want explicit control over the rendering.
Yeah, sometimes you just need to override it.
And that's where the advanced customization options come into play. If you're using the Lightbox, you can pass configuration variables directly in the script tag to align it with your brand. You can map a data primary color to your brand's hex code. You can toggle between a bootstrap or material data theme, and you can customize the header copy using data instruction text.
But the inline integration offers much, much deeper overrides. You can completely disable the style sniffer if you want to and pass explicit JSON strings into the configuration attributes.
Right.
You provide a JSON object to data custom $celeste for the default CDO, data focus cease for the active state when a user clicks into the iframe, and data valid lists or data invalid Cs to handle real-time validation feedback.
But there is a catch here. There is a very strict, non-negotiable whitelist of allowed CSS properties. You can't just throw whatever CSS you want into that JSON.
No, absolutely not. The documentation explicitly limits you to properties like color, background color, font family, font size, padding, border radius, and letter spacing.
basic box model and typography stuff.
Exactly. If you try to pass something like position absolute or z-index, opacity, or complex CSS transforms, the gateway completely ignores it. It literally strips it out before rendering the iframe.
And the security rationale for that whitelist is so critical to understand. Why do they lock it down so hard?
Because if a merchant site is compromised, or if a rogue third-party dependency tries to inject malicious configuration data into the Collect.js initialization, allowing arbitrary CSS would be disastrous.
How so? Like, what's the attack vector?
Well, an attacker could use opacity 0 combined with position absolute and high z-index values to overlay the invisible gateway iframes directly on top of harmless-looking buttons on the merchant site.
Click checking.
Exactly. It's a classic UI redressing attack. The user thinks they're clicking a button that says, claim free gift or accept terms, but their browser is actually executing a click inside the invisible payment iframe.
That is terrifying.
It is. So by aggressively restricting the CSS to purely typographic and basic box model properties, the gateway ensures the structural integrity and visibility of the secure enclave. It can never be compromised by the host page.
It's a fascinating trade-off. You get enough styling power to make the fields look native to your design system, but you are physically prevented from executing any layout manipulation that could weaponize the iframe.
It's the only safe way to do it.
Beyond styling, you also need programmatic control over the tokenization flow, right? Especially in single-page applications, SPAs, where you don't really rely on standard HTML form submission events anymore.
Right, you're usually handling state with React or Vue or something.
Exactly. Collect.js exposes the Collect.js.startPaymentRequest function. You pass it the event, and this allows your front-end code to manually trigger the validation and tokenization process based on any custom logic or state change in your application.
And that programmatic control is paired with an extensive callback system, which is essential because, again, your local application is entirely blind to what's happening inside those iframes due to the same origin policy.
Right, it's a black box.
Exactly. So the data validation callback is incredibly chatty. It provides real-time state updates. As the user types into the localized iframe, Collect.js fires this callback, returning a JSON object detailing exactly which fields are currently valid or invalid based on its internal checks.
This is how you build those highly responsive modern UIs. Let's say a user is typing a 15-digit American Express number, but your local UI was somehow expecting a 16-digit standard format. Because the iframe knows it's an Amex based on the starting digits, it handles the validation correctly internally. If the user misses a digit, the validation callback immediately alerts your local JavaScript that the same number field state has shifted to invalid.
And then your front-end framework catches that event.
Right. It catches it and instantly reacts. Maybe by injecting a red border onto the parent wrapper div, or displaying a helper text span below the field saying, please verify your card number. The raw data remains locked in the iframe, but your local DOM can perfectly reflect the validation state to the user in real time.
You also have to engineer for network degradation.
Oh, always.
Think about what happens when the user clicks submit. Collect.js reaches out to the gateway to generate the token, but the user's mobile connection drops as their train enters a tunnel.
The dreaded infinite loading spinner.
Exactly. You can't leave the UI in a perpetual loading state. The data timeout callback allows you to define a specific duration in milliseconds. If the gateway doesn't respond with the token within that window, the callback fires.
And your application can catch it, dismiss the loading spinner, and gracefully prompt the user to check their connection and try again. You maintain total control over the UX even during a network failure.
The callback that really shows off the framework's polish, though, is the data field's available callback, specifically how it exposes blur and focus events.
Yes. This is my favorite part of the implementation.
If you are implementing a material design interface, you rely heavily on floating labels.
Right, where the placeholder text sits in the middle of the input, but when the field gains focus, that text animates up to become a small label on the top border.
Exactly. To orchestrate that CSS animation on your parent container, your local DOM needs to know precisely when the user's cursor is inside the secure iframe and when it leaves.
Because normally you just attach an on-focus listener to the input, but you can't touch the input.
Right. So Collect.js broadcasts a focus event the moment the user clicks in, allowing your local JavaScript to trigger the upward animation. When the user clicks out, it broadcasts a blur event. But the crucial detail is that the blur event payload includes a simple Boolean flag, empty true or empty false.
Which is the exact piece of data you need to resolve the UI state. You can't check the value of the field to see if they typed anything because of the same origin policy. You can't ask, hey, iframe, what did they type?
No, the browser would block that immediately.
But because Collect.js explicitly hands you that Boolean, your local logic knows exactly what to do. If the blur event fires and empty is true, your script removes the active class, and the floating label smoothly drops back down into the placeholder position.
And if empty is false?
If empty is false, it means they left data in the secure field. They typed their card number, so your script leaves the label floating at the top. You get to build a complex, state-dependent CSS animation around a black box iframe without ever violating the security boundary. It's just incredibly elegant engineering.
It really demonstrates a deep understanding of modern front-end requirements.
Mm.
However, as robust as these iframe implementations are, relying on users to manually input 16 digits, an expiration date, and a CVV is rapidly becoming an anti-pattern in e-commerce.
Oh, for sure, especially on mobile devices where typing friction directly correlates with cart abandonment. You force me to type on my phone, I'm probably just going to close the tab.
Exactly. And this is why the integration of digital wallets is perhaps the most critical capability of Collect.js today.
Let's break down the Google Pay integration first. The premise here is to leverage the payment credentials and shipping data the user has already securely stored in their Google account, whether they are authenticated on an Android device or using Chrome on a desktop.
Right, and setting it up requires minimal configuration on the Collect.js side. You initialize the script with data country and data currency variables.
Which is necessary, so the Google Pay sheet can filter the users of available cards, right?
Yes, exactly. It ensures it only presents options valid for that specific transaction context. Then, you drop an empty div into your DOM with an ID like Google Pay button, and Collect.js renders the native interactive wallet button directly into that space.
The customization is pretty straightforward. You can adjust the button color to match your layout, maybe localize the text to display Buy with GPay or Subscribe, but the architectural advantage lies in the data payload.
Because Google Pay isn't just a secure card vault, it functions as a comprehensive identity and logistical data provider.
Right. By adding a few extra data attributes to your Collect.js configuration, like setting data field Google Pay shipping address required to true, or requesting the billing address, email, and phone number, you completely alter the checkout flow.
The user taps that button, the OS-level Google Pay sheet slides up, the user sees their default card, their default shipping address, their contact info.
They authenticate with biometric Touch ID or Face ID, and Google passes that entire encrypted payload back to Collect.js. The user literally bypasses your carefully designed HTML web forms entirely. They don't type a single character.
From a back-end engineering perspective, the absolute brilliance of this workflow is the normalization of the payload.
Yes, talk about normalization, because this saves so many headaches.
Your server-side payment API integration doesn't need to know how to parse a complex encrypted Google Pay data blob. Collect.js ingests that encrypted payload from the wallet, communicates with the gateway, and outputs the exact same standardized payment token format we discussed earlier.
It's amazing. Your local JavaScript receives the identical string format, whether the user manually typed their Visa into the inline iframes or biometric authenticated through Google Pay.
You just pass payment token to your backend. The gateway recognizes the token's origin, decrypts the underlying Google Pay payload using its private keys, extracts the PAN, the requested shipping address, the email, and injects all of that into the transaction record.
But this creates a really fascinating scenario regarding data hierarchy and state management.
Oh, the conflict resolution.
Right. Suppose a user starts filling out your local HTML form. They enter a shipping zip code to calculate an estimated delivery cost. Then, they decide to abandon the manual entry and click the Google Pay button to complete the purchase.
Right.
The zip code they typed into your local DOM might conflict with the zip code stored in their Google Pay profile. When your backend submits the transaction, sending both the local form data and the Google Pay token, how does the gateway know which one is right?
The gateway enforces a strict hierarchy. It actively strips out your locally submitted data and overrides it with the data extracted from the Google Pay token. The wallet data always wins.
Always wins, and that makes perfect sense from a trust perspective, doesn't it?
Absolutely. The data payload inside the Google token was explicitly authenticated by the user via biometrics just milliseconds prior to the transaction. It is the most verified, highest fidelity source of truth available, so the gateway discards the unverified local DOM state in favor of the wallet state.
That behavior just simplifies the merchant's backend logic so much. You don't have to write complex reconciliation algorithms to determine which address fields to prioritize. The gateway just handles it.
Exactly. Now, while Google Pay handles the Android and Chrome ecosystems pretty seamlessly, adapting to the Apple ecosystem requires navigating a much more stringent set of security protocols.
Apple Pay is notorious for its strict deployment requirements, and Collect.js has to facilitate all of them. While the visual setup is similar, providing the price, country, and currency to render the black Apple Pay button, you cannot simply initialize the script and expect it to work.
Not at all. Apple demands cryptographic proof that the merchant explicitly controls the domain where the payment sheet is being invoked.
And this is where the domain verification file comes in.
Right. The developer must log into the payment gateway's control panel, download a specific text file containing a verification hash, and deploy that file to their production web server.
And it has to be in a very specific place.
Crucially, it must be hosted in a hidden directory at the root of the domain named .well-known.
Right, .well-known.
Once the file is live and publicly accessible at that exact path, the developer registers the domain in the gateway. The gateway servers communicate with Apple servers, which then make a direct HTTP request to your domain to read that verification file.
It's a huge handshake.
It is. And only after Apple successfully reads the file and validates the hash will the Collect.js script be authorized to render the Apple Pay button on your front end.
It's a rigorous process, but it completely neutralizes domain spoofing attacks. An attacker can't just scrape your front-end code, host it on a phishing domain, and trick users into authenticating an Apple Pay session, because Apple will literally refuse to render the payment sheet on the unverified domain.
Exactly. It protects the ecosystem.
Once you clear that deployment hurdle, Collect.js provides incredible depth for customizing the Apple Pay interaction. Like, you can pass a JSON array into the configuration called data field Apple Pay shipping methods.
And this completely revolutionizes the mobile UX. Instead of forcing the user to select their shipping speed on your web page before clicking the Apple Pay button, you populate the native Apple Pay sheet with the options.
So it all happens inside the Apple interface.
Right. The array contains the labels, the prices, and the identifiers for, say, standard shipping, expedited, or next day air. The user taps their preferred method directly within the iOS interface. The total price updates dynamically on the sheet, and the selected shipping identifier is packed into the final token payload.
But dealing with the resulting Apple Pay token introduces a massive architectural caveat. And backend engineers really have to understand this, especially for subscription-based business models.
The cryptogram issue.
Right. Apple Pay tokens are structurally different from standard tokenized credit cards. They contain a time-sensitive cryptogram that is bound to the specific transaction amount and the exact moment of biometric authentication.
The documentation is incredibly explicit about this. You cannot save a raw Apple Pay token directly to a customer vault to run arbitrary charges weeks or months in the future.
Right. If you attempt to vault the raw token and then initiate a charge 30 days later for a subscription renewal, the gateway will just reject it because the time-sensitive cryptogram has expired. The cryptographic proof that the user was present and authenticated the charge is no longer valid.
So to facilitate recurring billing models, Collect.js has to orchestrate a very specific workaround authorized by Apple and the card networks.
Walk us through that because it's super clever.
It leverages a suite of recurring variables. You configure Collect.js with data field Apple Pay recurring description, defining the terms of the subscription, along with the start date, the billing interval, and the end date.
So the user sees all of this when they double-click the side button.
Right. When the user triggers the button, the Apple Pay sheet displays these exact recurring terms. But here's the critical maneuver. Collect.js defaults to constructing this initial payload as a $0 authorization.
A $0 auth. Okay, so how does that help vault the card?
When the resulting token is passed to your backend and you submit it to the payment API to vault the customer, the gateway executes an immediate $0 authorization against the card networks using the fresh active cryptogram.
Got it.
This action immediately validates the user's biometric approval, it registers the recurring billing agreement with Apple and the issuing bank, and it establishes a vaulted credential that is explicitly flagged for future merchant-initiated recurring charges.
And the actual monetary charge, like the first month's subscription fee, is deferred until the agreed-upon start date.
Exactly. It cashes in the cryptogram immediately for a valid vault record. It effectively unlocks your ability to charge the card on file later without requiring the user to look at their phone again.
It's a brilliant technical negotiation to satisfy Apple's strict privacy constraints while still supporting modern SaaS and subscription business models. And Collect.js even handles the ecosystem fragmentation, which is wild.
Yeah, because Apple only introduced these specific recurring APIs in newer operating systems.
Right, so the framework actively checks the client's environment. If it detects that the user is running an OS older than iOS 16 or macOS 13, it knows the native recurring payment sheet isn't supported.
And instead of just failing silently or throwing a generic error, it fires a data Apple Pay recurring mismatch callback.
Which empowers your local application to intercept the failure. Maybe you render a tooltip asking the user to update their device. Or, more practically, you seamlessly unmount the Apple Pay button entirely and reveal the standard inline credit card form so you don't lose the conversion.
The level of fallback logic is just phenomenal. Think about the entire architecture we've covered today.
That's a lot.
Whether your user is typing a 16-digit PAN into a seamlessly styled iframe that perfectly mimics your DOM, or tapping a Google Pay button to bypass your form entirely, or using Face ID to trigger a complex $0 recurring authorization via Apple Pay Collect.js, normalizes all of that chaos.
It really does. It translates every single one of those distinct user interactions into a singular, standardized, highly secure token that your backend API inherently understands.
It acts as the ultimate abstraction layer. It empowers front-end teams to build highly responsive, localized, and conversion-optimized interfaces, while simultaneously allowing the back-end engineering teams to completely wash their hands of PCI-compliant scope and raw data liability.
So if you are an engineer or an architect listening to this right now, audit your payment flows. Seriously. Look at your code. If you are handling raw PAN data, if your state management libraries are storing CVVs even temporarily, or if your backend is logging full credit card numbers in a debug file somewhere, you are managing a massive unnecessary risk profile.
You're just waiting for a breach.
Exactly. Implementing a framework like Collect.js to handle the tokenization at the absolute edge of the client side isn't just a UX upgrade. It is a fundamental security imperative for your organization.
And the trajectory of this technology raises a really compelling architectural question for the future. As abstraction layers like Collect.js and biometric digital wallets become universally adopted, we are rapidly approaching an ecosystem where the merchant fundamentally never handles the financial data they are processing.
Ever.
Right. If every single transaction is executed via a temporary, single-use, cryptographically bound token, the digital liability footprint of a merchant effectively drops to zero. We really have to consider whether we are architecting a web where the very concept of stealing a credit card from a merchant database is engineered out of existence entirely.
A completely abstracted ecosystem where the payload is useless the moment it's generated. That's an incredibly powerful architectural goal to aim for, something to definitely mull over as you build out your next checkout flow. Keep analyzing your dependencies, keep auditing your data flows, and we'll catch you on the next deep dive.